All right, so we've gone over generally what the equilibrium constant K is the ratio of products over reactants. More specifically, for a given reaction, they are generic AA plus BB equals CC plus DD. The equilibrium constant is represented as such, where alpha is the activity of a chemical. I won't go in depth on the physical meaning of activity, but I will say that for different phases, the activity means different things. And so, in short, the activity of an aqueous solution is its concentration. Same goes for a gaseous phase. And then for solids and pure liquids like water, for example, activity is just equal to 1. That means then that all of our equilibrium expressions will only include the products or reactants that are aqueous or gaseous and ignore the terms which are solid or liquid. So let's assume all the chemicals in my example reaction from above are solutions or gases. Now, using concentrations instead of activities, we have Kc. The Kc here is just to specify that we're using concentrations of products and reactants in the usual units of moles per liter. But what if we're given pressures and not concentrations, like we usually would for some kind of gas? Do we need to convert every partial pressure into concentrations? I mean, we can using the ideal gas law and rearranging it so that N over V is equal to concentration, right? And then that's equal to P over RT. But that can be really time consuming if there are many products and many reactants, and frankly, we don't have to. Instead, we can use Kp, the equilibrium constant of pressures, which looks just like our previously shown Kc, but with partial pressures instead of concentrations. Note here that pressures must be in units of atmospheres. Now, Kp and Kc are not equivalent, and Kc is really the more commonly used and proper equilibrium constant, but they're mathematically related fairly easily. This relationship is also based off of the ideal gas law, but I won't go through the full derivation here. If you really want to see the math, you can check out chapter 14.3 in the textbook. But in any case, the relationship is Kp equals Kc times RT to the delta N power, where R is the ideal gas constant in the proper units of liters, atmospheres per mole Kelvin. T is the temperature in Kelvin, and delta N is the difference in stoichiometric equivalence between the products and the reactants. Mathematically, drawing back to our example reaction, right, we can define delta N as such: the molar equivalence of the product minus the molar equivalence of the reactant. So as I said before, Kc really is the preferred representation to describe equilibria, as it can more directly describe the relationship between products and reactants. Remember that Kc much greater than 1 indicates that the products are favored, and a Kc much less than 1 indicates that the reactants are favored. But the same cannot necessarily be said of Kp, right? So you can test that out with your own various equilibria, but trust me, it's not always cut and dry like that. And so also gases can be represented as pressures and as concentrations, but solutions are restricted to only being concentrations. So that's why we would generally prefer Kc to Kp.